In the last section, we talked about solving systems by graphing. Today, we are going to talk about solving them algebraically, which when we say algebraically, that means you're just manipulating equations and you won't actually be graphing anything. We're going to learn two different ways to do them algebraically, one in this lesson and then one in 3.5. So just a reminder, what are systems, or what is a system? It is just two or more equations that you solve at the same time. Systems generally have two variables and two equations. That's what we in Algebra 1 solve. Before we actually start solving, we're going to start incorporating some word problems and figuring out how to write variables and equations for them. So in example 1, Monica built a porch that contained two different colors of bricks to create a nice pattern. She purchased the red bricks at $2 each and the gray bricks for $3 each. How many red bricks did Monica purchase if she spent $160 on 60 bricks? So hopefully, without any of this stuff down here, you would have recognized that there's two different things we don't know. We don't know how many red bricks, and we also don't know how many gray bricks. If you're not sure what your variable should be, what you're trying to solve for, read the last sentence. The last sentence is the question, almost always asking you to find something. In this case, it is saying, how many red bricks? So we are looking for the number of red bricks. That has to be one of your variables. So you can choose any letter you want to give it. I am going to give it R. R for red bricks. Okay. That's the only thing they ask you to find, but as you read the first two sentences of the problem, you realize that there's something else that they're talking about, and that is the second color of brick, which happens to be gray. We don't know how many gray bricks she bought either. We're not asked to find it, but it is an unknown quantity, so we need a variable for it as well. Generally, when you're solving a systems problem, you're going to have two variables. Okay, so figure out what those two variables would be. So first thing we did, we found our two variables. We defined them. In other words, you write the letter and then you write what it represents. Anytime you're doing a word problem, you need to define your variable. If I just called these X and Y, I wouldn't know which one was red and which one was gray. Okay, so you always want to specify. It's fine to call them X and Y, but you would want to write which one is the red bricks and which one is gray bricks. Also, be very specific what you're talking about. You don't want to just say R equals red bricks. What about the red bricks? Are we talking about the cost of the red bricks, the amount of the red bricks, how many there are? So we want to be real specific in talking about what the variable is. So it is the number of red bricks and the number of gray bricks are our two variables. Okay, we need to come up with equations. It's a system, so you should be thinking about two equations. They give us some different numbers. So the two different colors, I don't think we need that information anymore. We took care of that with our two different variables. But information that is going to be useful to us, red bricks, $2 each, and gray bricks are $3 each. Okay, we also know she spent $160 on 60 bricks. Okay. So thinking that through, if she's spending $2 for each red brick, to find the total amount she spent on red bricks, I would have to take $2 times however many red bricks I got, or Monica got. But she didn't just buy red bricks, she also bought gray bricks, so I would have to add to that amount $3 for each gray brick. So this is the amount of money she is spending, and we happen to know that that is a total, so equal to 160. Okay, well, I never used the 60 bricks part. Well, the 60 bricks didn't have anything to do with the amount of money. So I kept this equation as all about the amount of money. $2 times each red brick plus $3 times each gray brick gives me a total of $160. My second equation, I just want to deal with the total amount of bricks. Well, I know the total amount of bricks is going to be 60. What would I have to add up to equal 60? It doesn't have anything to do with the dollar amounts. It's simply however many red bricks Monica bought plus the number of gray bricks she bought would have to equal 60. So maybe she got 30 and 30 for a total of 60. Maybe she got 40 red bricks and 20 gray bricks for a total of 60. If we solve this system through, we would find out exactly how many red and gray bricks she bought to have a total of 60 bricks and a total dollar amount of 160. At this point, we're not solving. I'm just wanting you to set up the equations from the word problem. So we will stop there, and we will look at example 2. A boat traveled 144 miles downstream and back. So we've got a boat, we've got a current, a little river maybe. Here's my red water. That's a little frightening. Maybe should have made that blue. You've got a boat on it. There's my boat. And it is going to go downstream and then back. Okay, 144 miles each way. Okay, so each route is 144. The trip downstream took 4 hours. Ooh, wait, am I reading that correctly? A boat traveled 144 miles downstream and back. I'm thinking that's supposed to be the total. That's not a very clearly written. I apologize for that. So let's say the total trip there and back is 144 miles. The trip downstream took 4 hours, so just downstream 4 hours. And the trip back took 8 hours. Well, why would that take longer? Think about if you're traveling downstream. The current is pushing you downstream. Okay, so the water's flowing downstream. So it's going to make you go faster. Versus when you would be traveling upstream, you're working against the current. So you have to work harder. The current's pushing you the opposite way of the way you're trying to go. So it takes longer. What we want to figure out is what is the speed of the boat in still water. So if we didn't have that water current working either with us or against us, if the water wasn't moving at all, what would be the speed of the boat? Okay. To define your variables, now obviously I have told you what they should be equal to, but if you were doing this problem on your own, you could look at that last sentence. It's going to give you at least one of your variables. And here it is, the speed of the boat in still water. Okay, so speed of the boat, and you could write in still water if you wanted to. I'm going to call that B for boat. You could have called it S, you could have called it X, you could have called it any letter you want. The other thing that you don't know, while they don't ask for it, is the speed of the river's current. Okay, because we would have to get rid of that to figure out the speed of the boat in the still water. So I'm going to call that C for current. So the first two things you need to do is figure out what you are looking for, 2 different things, give those variables, and write them down. And then we need to come up with our equations. Okay. They're telling us the boat traveled 144 miles downstream and back. So let's see what we can do with that information. To set up these equations, you're going to need to know the formula. D equals RT. Hopefully you've gotten to this in science class. If you haven't yet, you will do this. You will work on this year. But that stands for distance equals rate times time. Distance equals rate times times. Times time. Distance equals rate multiplied by time. There you go. So if you're looking at your total miles, we have 144. And now that I'm reading this again, it is supposed to be 144 each way. Sorry for the confusion with that. It should be more clear there. I'll try to make the rest of the problems clear. 144 miles is a total, so that would be your total distance. Equals, let's come back to rate for a second. What's the first time we know? First time we know is 4 hours, so at the end we're going to multiply by 4. That's the trip that is downstream. When you are a boat going downstream, are you working with the current or against it? Hopefully you said with. The current would be pushing you downstream. So our rate here would be the speed of the boat plus the speed of the river's current. And again, that's because the current is pushing you. It is helping you get downstream. Okay, so your distance was 144. Your rate is the speed. Rate and speed are very, you could put those together in this problem. So you could also think of that as your speed. Well, your total speed would be the speed of the boat plus the speed of the river's current times your time, which is 4. Okay. Pause the video here and see if you can come up with a second equation. Okay, the second equation also uses d equals rt. Your distance is still 144. It's the same distance both ways. We finally figured that out. And your time is 8 hours. But on this one, your rate, you're working against the current. Okay, so you would have to take the speed of the boat and subtract the current. It is working against you. Okay, these two examples are kind of typical examples of what they ask you to do with systems. This one I think of always as amount of money and then amount of items. And then this one just uses that d equals rt. When you're working in these with the rates, you have to think as the downstream one, or sometimes it's with air speed. One is going with you in one direction, and in the other direction it's going against you. So you'll add in one, subtract in the other for your rate, but it's always d equals rt. Okay? And then we could actually go through and solve these to find our answers, but for now, that's all I wanted you to do. Okay, moving on. Remember, there are 3 types of solutions to a system of equations. The first one is one solution. That one solution is the point of intersection. It's the point that the two lines would have in common. It must be given as an ordered pair. The second type of solution would be no solution, and you could get no solution when you have parallel lines. And the third type of solution you could get would be infinite solutions, and that occurs when you have the same exact line. Keep in mind that doesn't mean every point would be a solution to that system, just the points that would be on that single line. Okay, let's get into solving these in our new method called substitution. We're going to talk about 3 steps to get there. Step 1, solve one equation for one variable. So you'll have 2 equations, and each equation will have 2 variables. You get to pick which one of those you want to solve for. So choose any one variable and solve for it. And when we say solve for the variable, it means get that variable by itself, get it isolated. I'll give you some tips on how to pick the easiest one to do it as we go through the problems. Step 2, substitute. Here comes that name, substitution. Substitute what you solved for in step 1 into the other equation. and solve. Okay. And then step 3, substitute. Here's another substitute. Substitute that number that you found from step 2 into either equation and solve again. So notice you're substituting twice and you're solving twice. It should make sense to you that you're solving twice because the solution to your system is going to be an ordered pair, so you would have to solve for the x and solve for the y. Okay, let's try one. Example 3 here. Let's cover some of this up, make it easier to look at. So I'm telling you right away, there's going to be one solution. Okay? Step 1, solve one equation for one variable. So you have 4 choices. You have this x, this y, this x, or this y. If you look at all 4 of those options, one of them is easier than all, one of them is easier than all the others. Think about which one you think would be the easiest to solve for. The easiest one to solve for is this x because it has no coefficient with it. Okay? You could do it for any of them and they would be perfectly fine. However, the easiest one, which is generally going to be the one that's going to lead you to the least mistakes, is this x. So how would you get that x by itself? You would subtract 6y. So x equals 4 minus 6y. It does not matter what order you put this stuff in over here. You could do negative 6y plus 4. Does not matter. That's step 1. Step 2 now, you're going to take what x is equal to, so 4 minus 6y, and you are going to substitute it in to the other equation. So not the second equation, that's what we already worked with. Substitute it into the other one in place of x. So I'm still going to have 4, but in place of the x, I am going to, in parentheses, put in 4 minus 6y. And then I'm going to continue writing the rest of my equation. Okay, so I just took the x out and I replaced it with what I found x to be equal to, 4 minus 6y. At that point, if you look what you have, you now only have y's in your equation, no more x's. So this is one equation with one variable, and that's solvable, just like you were doing in chapter 2. I would start with distributive property. Then I would combine like terms. These y's are on the same side, so I combine them exactly as they are. Negative 27y, subtract 16, and then divide by negative 27. Y equals 1. Yay, we have an answer. And you might get real excited and think you're done with the problem, but that was only step 2. Keep in mind your solution needs to be an ordered pair, and at this point we only have one of the pieces of the ordered pair. Good news is the third step goes much quicker than the second. You're going to take your answer and substitute it into either one of the original equations. You can choose whichever one you think might be easier. To me, the bottom one looks easier because I don't have any subtraction. So I'm going to write that equation, but in place of the y, I'm going to plug in 1, since y and 1 are equal to. You are allowed to substitute that. Then I'm just going to keep solving. So I get x plus 6 equals 4. Subtract 6, x equals negative 2. Then I can go ahead and fill in the rest of my ordered pair. How could you check this? Well, you could plug it into both equations, make sure it works in both. You should get negative 11 on both sides in the first one. You should get 4 on both sides in the second one. and that will in fact work. You could also graph it either by hand or in your calculator and make sure that that's what you would get. In order to do that, of course, you would have to get it in a slope-intercept form, so it might just be quicker to plug it by checking or check it by plugging in. All right, let's try another one. In this example 4, I think you have one variable that would be easier than the others to solve for. Which one do you think it would be? You might think either one of these b's, but this b technically has a negative 1. This one's a positive 1, so this one would be the quicker one to solve for. Nothing wrong with solving for any of the others. This would just be the quickest. So I'm going to rewrite that. To solve for b, I would need to get rid of the 2a. It's positive, so I would subtract it. b equals negative 8 minus 2a. That's step 1. Step 2, I'm going to substitute it into my other equation. So pay attention to which equation you worked with the first time, because you always need to use the second equation, or the opposite equation, the second time. So 4a minus, instead of b, I'm replacing it with what b is equal to. It's equal to negative 8 minus 2a. And then I have equals negative 4. Okay, one equation should remain with one variable. So I need to distribute the negative sign. 4a plus 8 plus 2a. I am left with like terms on the same side. 4a plus 2a is 6a plus 8 equals negative 4. Subtract 8 on both sides. 6a equals negative 12. Divide by 6, and I get my answer for a of negative 2. Okay, that's step 2. For step 3, take that a equals negative 2 and plug it back into either of the equations. Okay, so steps 1 and steps 2, you have to use different equations. Step 3, you get to use either equation that you want, whichever one. I'm going to pick the top one. So 2 times, not a anymore, I know what a is, it's negative 2, plus b equals negative 8. So I get negative 4 plus b equals negative 8. And then adding 4, I get b equal to negative 4. So my ordered pair, if they don't tell you any information about it, you just want to do it in alphabetical order. Negative 2, negative 4, a then b. All right, you guys go ahead, pause the video, and try example 5 here. All right, check your answer there. I got 0, 4. I labeled where I was done with each step, so check the ends of each step and see if you have what I have. You may have chosen to solve for a different variable from the beginning. That should not affect your answer. Okay, if you are getting a different answer and you chose a different variable, you have made a mistake somewhere else. It's not in choosing your variable. When you substitute in, make sure you include the whole equation except for the one variable that you are solving for. The coefficient still should be there. It's just the variable that comes out and you replace it. Don't be afraid of 0 here. Sometimes you guys see 0 and you think it's no solution. 0 is a number just like any other number. You still have a variable, so you need to keep solving. It's just so happens your answer comes out to 0, which is perfectly fine. Plug that in, either equation, and get 4 for your y. Make sure if you made a mistake, you know where and you fix it. All right, not to mention, by the way, this couldn't have been no solution because I told you up here. Hello, it's one solution. All right, but that brings us to a no solution. So let's see what that would look like. The variable that would be easiest to solve for is the one that does not have a coefficient, which is that y. So we need to add 3x on both sides. Y equals 3x plus 4 or 4 plus 3x, does not matter. And we have y solved there. So we are going to take that stuff and plug it into the other equation for y. So that would be 3x plus 4 equals 3 still. And then it's just a matter of solving. So we're going to distribute. We get negative 6x minus 8 Oh, and look at this. We have 6x minus 6x. Well, that's 0, so that cancels. That's gone. What we're left with then is negative 8 equals 3. Is that a true statement? No. Those do not actually equal. So when all of your variables cancel and you end up with an equation that does not work, that's when it's going to be no solution. It's very similar to when we were solving one equation and this happened. Okay, so to have no solution, all variables cancel and you're left with a false statement. Not statement, how about a statement? Okay, that is how you would get no solution. Make sure you write that down somewhere so you remember. That is how you get no solution. Notice that it is not because of a 0. 0 is a solution. It's because everything, all of your variables are gone, and your statement that you're left with is not true. Okay, you guys try number 7. See what happens to make infinite solutions. Pause the video, give it a shot. Okay, check it out. Sort of the same thing happens as in no solution, but slightly different. So I chose to solve for this one. That would be the easiest variable to solve for, but of course it's not wrong if you solve for a different one. I substituted it in, and as I was solving, all of my variables canceled. Negative 6y plus 6y canceled, and what I was left with was a true statement. Negative 15 is equal to negative 15. That makes it infinite solutions. So anytime you have all variables cancel and you're left with a true statement versus a false statement, true gives you infinite solutions, false statement gives you no solution. In the last chapter, when we ended up with infinite solutions, we were giving the all real numbers symbol. There is a difference between these two answers. All real numbers means any number that you could think of will be a solution. Infinite solutions means there's an infinite amount of solutions, but it's not saying everything is a solution. Because remember, for a system, the solutions would be just the points on that overlapping line. It wouldn't be all the points. It wouldn't be the points not on the line. So we don't want to say all real numbers. We just want to say infinite solutions. All right, that's all I got for you. Go ahead and finish your packet. Pay close attention or put some extra thought into writing the equations from the word problems. Okay? Go slow, do all of the problems, and check your work.